Hello everyone, welcome to chapters 23 and 24, which will go together as one exam. This chapter is basically about changes of phase. A lot of it, in fact, everything that is in these chapters you had in chemistry, but maybe not as in depth, okay? What I want you to remember is that at a given pressure, a substance, let's say water, and in this diagram, what we have here is uh, basically temperature as you go up, okay? And you can be time or heat or whatever, but as you go up here, you have temperature, and here you're at 0, and here you're at 100 Celsius. But point is, we have these diagrams where we have there are more than three phases of matter, but in general, there are three common phases of matter: solid, liquid, and gas, right? And there are even different types of solids and plasmas at the cold and the hot end, but we're not going to worry about those. When you go from one substance to another state, and I know like they use the word phase. I don't like to use the word phase. I prefer using the word state because phases are also used, particularly in chemistry, to talk about divisions between immiscible liquids. And then you have like multiple phases and even separation of soils by phases. So I think state is a better word for ice, liquid, or solid, liquid, and vapor. But we're going to talk about like what is it when you go from one to the other and different things. First of all, what I want you to understand though, and this is kind of a relationship to the kinetic molecular theory that's not really in the chapter, but it helps you to understand this chapter, is that particles have a certain amount of energy. And when we talk about temperature, like for instance, if right here, if this is 100 degrees Celsius, so this given amount of energy, the average at right here, uh, temperature is average kinetic energy. So if we say right here is, if the average is right at this point, then it's 100 degrees Celsius. Well, then water is going to boil. And what you'll see is the average particle has enough energy. 50% of the particles have more than enough energy to escape and become gas. 50% of them stay liquid. And as long as you keep putting in energy, you'll keep, when some of this over here leaves, if some of this liquid over here leaves, then you have more particles over here than you do over here, so the solution cools. The system cools when you boil. Boiling is a cooling process. The steam is hot, but the liquid actually cools down. That's why you have to keep applying heat when you're boiling something. But the point is, there are particles. It doesn't, when it's boiling, it doesn't mean that all of the particles have that amount, the required amount of energy. It means that half of them do and half of them don't. And when you cool down, you'll see that, yeah, the average goes down, but there are still some particles that have enough energy. And that's where evaporization takes part. Like there are some particles that have enough energy to become a gas, even though the solution on average does not, or system on average does not. So just remember that you can always, and boiling and evaporation are both types of vaporization. So the process of going from liquid to gas is vaporization, and you can do it by boiling, by evaporating. There are other ways of doing it. You can hit it with a bolt of electricity, which causes instant vaporization. There are lots of ways of doing it, but in general, it's the particles that have more energy that are leaving, which leaves the remaining solution behind cooler. All right. So let's go through this, and then keep in mind all the different phase change names. We can call this melting, we can call this freezing or fusion is another word that we can use here. So this is the process of fusion. Although the heat of fusion, if you remember back to chemistry, is actually ice to water, but that's the same. So the heat of fusion is this process. If you go from liquid to gas, that's vaporization. If you go from gas to liquid, that's condensation. And you probably already know that, but in like 7th grade, you're probably taught evaporization, condensation, precipitation. But really, it's vaporization is the general process. Just a few terms that you may not remember. If you go from a solid to a gas directly, which can actually happen if you have very low pressure. For instance, in space, there's always a little bit of sublimation that occurs where you can actually Astronauts speak of being able to smell uh, metal when they come back in from a spacewalk because some of the spaceship's particles are kind of creating this very, very dilute film of gaseous metal around the outside of the vehicle. But one that a lot of people don't remember is that if you go from a gas to a solid, that's deposition. And there are ways to do that with electricity and that kind of stuff. But really, I just want you to know the terms. Okay, and then I'll get to this down here later. So changes of phase is what we're talking about. When you change phase, there's energy that's involved. So right here, energy is involved in changing the phase. This chart here, I didn't write a label down here, but this could be uh, temperature. I could also say energy. I could also call this energy going up. And this is usually time or some other variable down there. But the point is, as the energy increases, it goes from a solid to a liquid to a vapor. Vapor has more energy. The particles are moving more. And in order to do this change, in order to go from a liquid to a solid, that energy has to come from somewhere. The energy has to be transferred, usually from, like you ignite some gas or an electric stove and then you put it on there and the stove is supplying the heat. So the heat's coming from outside the system into the liquid system, and that's what's causing vaporization. So solid, liquid, gas, plasma, there are more than one type of plasma, but the basic types of matter you know. So what do we want to talk about first? Well, we're going to talk about evaporization first. Just the first section is just about evaporization. And the first thing to remember is that it is a cooling process. That's why you sweat. The sweat cools off of you and it cools you down. You actually, and I don't understand that it's cooling the liquid left behind. I don't like saying just that it's a cooling process because evaporization cools, like let's say it's your sweat. Your body is cooled, but technically the environment around you is warmed because the environment around you is getting the higher energy particles and the lower energy particles stay with you. So you cool down, the air around you actually heats up a little bit. So this is a good wording that the book uses. It's a process that cools the liquid left behind. So it's evaporation technically is a change of phase from liquid to gas that takes place at the surface. So another thing to keep in mind, like you have evaporization, and this is going to be at the surface. And when we get to boiling, this actually happens throughout. Yeah, I know I use shorthand throughout, but boiling, once you reach a high enough temperature, boiling occurs everywhere. Although it does occur more at the source of heat. That's why you tend to see bubbles forming at the bottom of a heating pan, because that's where the heat is. So that's where the highest energy particles. So that's where boiling is occurring the most, at least at the start of boiling. But you'll also see the bubbles forming at the surface. And just quick trivia now, when you boil something or when you evaporate, you know how you get bubbles when you're boiling. And a misconception is that those bubbles, and we talked about this in chemistry, that those bubbles have air in them. But think about that. How do those bubbles form at the bottom of a liquid? How did the air get down there? It didn't. What's happening is the liquid at the bottom, if it's water boiling, then that bubble is pure water gas. There's no air in it, it's just water gas. When it bubbles to the surface, that water gas is released into the atmosphere as water vapor. So evaporization occurs at the surface and it's a cooling process. First two concepts there. And I've already talked about the kinetic energy part. Here's a little neat thing, like cloth covering the sides of a canteen. Why would you do that? If you take a canteen with cloth around it, which is why they're better than just the straight up metal ones, although you'll see the military ones that have like the harder plastic around them. If you get that wet and it evaporates over time, it'll actually keep the water inside of it cool because evaporation cools down what's left behind. Fun fact there. So how does evaporation affect a liquid's temperature? Well, if the liquid that's leaving is hotter, so the liquid left behind is cooler. It cools down what's left behind. Now the reverse process, going from a gas to a liquid, is condensation. Condensation. So if vaporization cools the water, condensation actually warms it. Okay, so if you see a soda and you start to see water droplets forming on the outside of the soda, the reason for that is the soda is so much colder than the room around it that uh, gaseous water in the air condenses on the side of the container. So it's actually warming your soda up while it's cooling the environment. And condensation is changing of a gas to a liquid. And there are many ways that can happen. And actually, this is one reason why I don't know if the book talks about this, but let's say that I have a flask or a container full of liquid. Okay. Uh, Condensation and evaporization both occur at the surface. So what's happening is particles are they either have enough energy to leave, or there's a particle up here that has a low enough energy that it can be captured by the water. Normally, if it has a high enough energy, it'll just bounce off because collisions among gas molecules are mostly elastic. So it doesn't lose any energy, it just bounces off and goes back into the world. But if it has low enough energy, it'll be captured, right? And let's say that I have a container like this and it's open. When it's open, you're going to see more particles leaving than coming in. So that's why an open container will eventually all the water evaporates out. If I put a huge cork on this, so I seal it. So I've now sealed this container so the liquid can't escape. Initially, because there's not enough gaseous particles in here, initially evaporation will start. So you'll have more evaporation than condensation. But eventually the evaporization and the condensation will reach equilibrium and they'll occur at the same rates. So something to keep in mind there, if I seal a container, there's a common question that can be asked like, how does the gas pressure change inside of a sealed container? Well, initially, for a brief period of time, it will go up as evaporation occurs, but eventually it will stay the same because evaporation and condensation will eventually reach the same rate. It's not that they stop occurring, it's that they eventually occur at the same rate. So that's another type of question to know the answer to. Okay. And that's kind of what they're talking about. A whole bunch of examples there. So condensation. You can read through the slides on your own. I'm just kind of hitting the key points here. What about when any substance contains the maximum amount, right? So we call that saturation. So think about if I add salt to liquid, eventually I cannot add any more salt because it is saturated. You might remember that from the solutions chapter in chemistry. It's like chapter 17 or 18, okay? So the point is that if you can, that saturation of a solution, you can saturate air as well. You can saturate anything, right? So if I have water on the ground, which the earth has a lot of it, like 68% of the surface is covered by water, that water can go into the air. Eventually the air cannot hold anymore. And we call that saturation, when the air cannot hold any more of it. Now, the way that we measure the amount of saturation of the air with liquid, in particular water, is what you hear of as relative humidity. And the relative is important because humidity is just the absolute amount of water in the air, which we don't really have an easy way of measuring it. Because the amount of water that air can hold changes with temperature, right? Different temperatures of air can hold more water. Hotter air holds more water just because it has more energy, among other reasons. So relative humidity is how much it could hold, right, is the maximum. So that'd be 100%. So if it was holding the most that it could hold, that's 100% relative humidity. And they usually don't say the word relative on the weather broadcast, but that's what they're talking about. So relative humidity is not a measure of how much water there is. It's a measure of how much there is relative to the maximum. So at 100%, the air is saturated. Anything below that, it's less. And around 70% humidity is when you start to feel it. And in the winter, because the air is not holding, doesn't hold as much water, and there's not as much water in the air, you tend to have lower humidity, which is why it feels dry. There's just less water in the air. Okay. So what else do we need to know? I already said this, at high speeds, molecules of water vapor bounce apart and remain a gas. So if they have a high enough energy, they just hit and bounce and stay a gas. But if they have a lower energy, they can actually come together and kiss and be happy and become liquid. Okay, so condensation process. I've said this before, temperature is a measure of average kinetic energy, and in particular, it's translational kinetic energy, so know that. Temperature is a measure of average kinetic energy. So think, and this will probably be the slide I end this one on, is it correct to say that relative humidity is a measure of the amount of water vapor in the air at a particular temperature? No, because uh, it's a measure of the I think that depends on how you want to word it, but um, humidity is the amount of water vapor per volume of air. So uh, humidity is just how much water there is. Relative is how much there is compared to how much there could be. So humidity is just a number. How much water is there in the air? Relative humidity is a ratio. Uh, So relative humidity is not a measure of the actual water vapor, it's a measure of the ratio of vapor to maximum vapor. Although I could see really people arguing both ways on that one. Not the best question, but I would basically want you to understand what relative humidity, that relative humidity is a ratio of the amount of water actually in the air to the maximum that could be in the air at that temperature. Okay. So how does condensation affect temperature? Well, evaporation was cooling. Condensation is a warming, at least for the object that something is condensing on. Condensation warms you, but it heats up the environment that is losing the lower energy particles. It doesn't really heat up, it raises the temperature. And temperature is just average kinetic energy of particles. All right, so we'll stop there and I'll start back with 23.3 with the next video.